Hello, everyone. Welcome back to the AAS YouTube channel, and this is part of the good stuff. This is the AAS Journal Author Series, and I am super happy to have Olga Harrington Pinto with us today. Hey, Olga.
Hi, Frank. Hi, everyone. Thank you for having me.
Well, thank you for agreeing to talk about your very awesome PSJ article, which we'll get to here in a little bit. And I love that background. Where did that background come from?
Oh, thanks. It's from the NASA website. When they were doing the promotion work for JWST, they had some artwork done, and this really spoke to me.
Very cool. So does that mean that JWST is going to be observing flowers and bees and other things, or what is that?
Well, I mean, the flowers and bees are kind of to tie in like how we're going to be expanding our search for like whatever we find in the solar system and the universe, and just kind of like how it ties into life on Earth.
I thought maybe they were saying there was enough resolution there that we could resolve bees on an exoplanet. And they're going, that's very impressive.
Who knows? Maybe there are bees on a planet. Yeah.
Absolutely. And Olga, what's your geolocation? Where are you located at?
Oh, I'm in Fort Lauderdale right now.
Fort Lauderdale. Awesome. So Fort Lauderdale on this April 24th, 2023, as we record this, is probably well into its spring. Yeah.
Yes. Today we had quite a bit of rain around here, and it's already spring because the pollen is out.
Yeah, okay.
And my allergies are up. Yeah.
Says the person with flowers and bees in their background.
Yeah.
Very cool. Very cool. And I'm in Phoenix, and we're in our deep spring. So probably in another month another week or so, somebody will hit the power switch, and all of a sudden we'll be into the upper 110s or Fahrenheit or something like that. So.
Oh, but it must be nice to have all of like the flowers blooming and everything around there.
We were actually relatively wet this year. We had a very wet, winter, and so yeah, there's lots of the desert is in bloom. It's very pretty. It's awesome. Very cool.
Yeah, nice.
And Olga, what do you like to do for research?
So I like to study comets. In particular, I like looking at their carbon monoxide and carbon dioxide. I primarily worked with sub-millimeter telescopes and also near-infrared telescopes.
Very nice. Very nice. Oh, and what is your position there in Florida?
Well, my position right now, I just finished my thesis and I successfully defended.
Oh, well, Dr. Olga. Dr.
Thank
Olga.
you. Yeah.
Congratulations, Dr. Olga.
Yeah, thank you so much, Frank. Yeah, I haven't officially gone to the graduation ceremony, but I've done all of the harder work, I guess.
Yeah, right. Satisfying the thesis micrometer people and all that kind of stuff. Yes.
Yes. Yeah.
Very cool. And so let's get to the main event. Let's bring up this very awesome PSJ article. It is open access, people. You can go grab a copy for free in the open access era. A survey of CO, CO2, HTO, and H2O in comets and centaurs. And Olga, take us away.
Well, first off, I want to start by thanking my co-authors, Maria Womack, Jan Fernandez, and James Bauer. They were a really big part of making this paper possible, and also really big support for me in helping arrange everything and bring new ideas to the paper.
Lovely.
But essentially, I'll go over the abstract a little bit before I get into the deeper dive of the paper.
Okay, however you want to do it.
Yeah, so the paper focuses on 3 molecules in particular that were observed in comet Comet: carbon monoxide, carbon dioxide, and water. I start off by talking about carbon monoxide and carbon dioxide because currently, pre-JWST, when the paper came out, there wasn't that much facility in trying to get carbon dioxide measurements from comets. So it was very hard and very like limited resources to kind of get that information. And yeah, in this paper, as we'll explore together, you'll see how I went about trying to find the optimal amount that I could, and also trying to derive and separate the CO and CO2 to try to maximize it a little bit more.
Nice, nice.
Yeah, so for the CO and CO2 measurement, for the CO and CO2 measurements, I was able to get it for 25 comets. Nice. But I was also able to get even more comets when I looked at the water production rates for CO and water. I look at all types of comets. I look at Jupiter family comets, Oort cloud comets, Centaurs,
Mm-hmm.
Yeah. And just like a variety of objects.
So just for relative sake, is this the largest survey ever?
Yes.
CO?
Yeah.
There
So
you go.
this is currently the
I
it's
will toot
currently
your
the
horn
largest.
for you there. There you go.
Yeah, thanks. Not to brag. Yeah, thank you. So this is the largest survey compiled from everything that's available in the literature, as well as everything that I've been able to kind of pull out independently as well.
Nice, nice.
Yeah. And so I look at carbon monoxide versus water production rate, carbon monoxide versus carbon dioxide, and then carbon dioxide versus water production rate, and then carbon versus oxygen ratios as well. And also the carbon and carbon dioxides versus the area of the comet. So there's a wealth of knowledge in here for whatever you're looking for.
Nice. Very cool. Very cool. Okay.
So getting into some of the objects. So as I mentioned previously, since I looked at a couple of different or a few different types of objects, Jupiter family comets are pretty well known in the field, but they have a Jupiter kind of orbit, like they're inside Jupiter. Then we have the Oort cloud comets, which are a little bit further back, and they're like scattered way far out. As you can see, like 10,000 to 50,000 AU in our solar system, and they don't really have that many apparitions coming in close to the sun. Jupiter family comets, on the other hand, they have a pretty constant rate of coming in. And I also have some Centaurs in the paper as well. And the Centaurs come from the trans-Neptunian region. So right now they're in kind of a gateway region where they're transferring from like a further out orbit and a JSC orbit kind of thing. Yeah. Yes, I also look at HTCs, though it's like a very limited kind of sample size that I have for that.
Okay, there we go. Cool. Okay. I'm with you.
So looking at these objects, I wanted to see what would be a good way at looking at how our solar system would have previously looked like. And so based off of literature and what is available, three of the most abundant types of molecules that have been currently observed in comets are carbon monoxide, carbon dioxide, and water. Since those are the most abundant, it seemed reasonable to see what exactly those look like in the available comets that we have, to get an idea of how our solar system could have possibly looked like, but also what comets are looking like right now, and if there was any behavior between them that kind of seemed to show up. Yeah. So water is typically the most abundant out of the three of the molecules, and then CO and CO2 kind of battle for second place sometimes.
Okay.
Yeah. So if we scroll down a little bit more. So yeah, in table 1, you can see an idea of the objects where I looked at carbon monoxide and carbon dioxide in the 25 Comet Comets that you'll see later on. And I list out what the molecular transitions were that I saw, which comets in particular I was looking at, and also like the papers that I'm referencing in order to get those kinds of data. And I think it's important to note in the first one where we see, or the first column where we see the instrument type, that there's a variety of techniques. Like, so you have stuff from the radio and IR, UV, and even the optical. And so many different pieces were used to kind of mold into what we have here.
Very good.
And that's what I talk about a little bit more in the methods and analysis section, where I go into depth about like how I chose the values that I chose. Oh, sorry, do you have a question, Frank?
No, I'm with you. I'm just
sorry. So I just go into a little bit more depth about the techniques, and I explain exactly what the techniques are looking at and how I try to use those measurements in order to get at my own.
Good. Okay. Yes, I'm with you. That's an impressive list of instruments, I have to say.
Thank you. Yeah.
You don't often see that breadth of instruments. So it's very nice.
Yeah, thank you. And I mean, thank you to all of the people who took these observations and were able to get the time. Yeah.
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 Good.
Yeah.
Okay. So overview and let's.
And so in figure one,
Yeah.
I talk a little bit about the problem with why we probably don't get as many CO2 measurements as we could. So previously, the largest study of CO2 in comets was from Akari.
Okay.
Yeah, where they had about 18 comets. And that was impressive. And when we have Neowise and Spitzer data,
Oh yeah.
we kind of run into a problem that because Neowise and Spitzer use bandpass filters, it doesn't really separate the CO and CO2. So as you'll see in figure one, there's like a dashed blue line and a
Yes.
red line,
Mm-hmm.
and those represent Neowise and Spitzer bandpass filters and what they're observing. And so you'll see that it comprises both like CO2 and CO,
Yes.
but it doesn't separately distinguish them the way that like ISO did, like the spectra that's being presented in the figure, where you have like a very clear CO2 signal and then a very clear CO signal.
Yes. Okay. Yes.
And because of this, it's kind of hard to gauge exactly if you're seeing CO2 or CO in a comet, and you just kind of have to make an educated guess about what is the species that you're seeing.
Okay. All right.
Yeah.
Good.
And so
we can slide down. Ooh, that looks like contemporaneous.
Yes, and so this is, I guess, a little bit more of the technical aspect of all of the data that I compiled. So as you'll see in the first column, I give the name of the comet. In the second column, I give the date when the data was obtained. In the third column, I give the heliocentric distance of the comet from when it was observed. Yes. The TA in the fourth column is the true anomaly of the comet. Mm-hmm. And then the CO production rates, the CO2 production rates, and the water production rates follow in the fifth through seventh columns.
Yes.
And then I get into the production rate ratios in the eighth through ninth columns, respective to each molecular species. And then in the 10th column, I give 1 over the semi-major axis. And I do that because you'll see later on, I talk about dynamical ages, and the way that that's typically referred to is 1 over the semi-major axis.
Okay, all right.
Yeah. And the last column is just references.
Right. Okay, good. And this is a wide 2-page table, so do check that out, people.
Yes. Oh, and really quick. So in some cases, as I had mentioned in figure 1, how it was difficult to separate the molecular species. In equations 1.1 or equations 1 and 2, you can see that there are those two equations were how I went about trying to separate out CO2 when it wasn't possible to get it directly. So one of the objects that was looked at was comet C2016R2. Okay. And that comet was observed with Spitzer. And what we had done is the team that I had worked with Maria Womack and Kasper Wierchos, we were able to get time with SMT to look at R2, and we were able to get a CO measurement from that.
Nice.
So we were able to subtract, well, first we assumed that everything that we got from Spitzer was all CO. Okay. So that production rate was assuming it was all CO, and then we subtracted what we got from the SMT measurements. Okay. And then we got some residual amount of CO. So once we subtracted those two, we had some left over. Okay. So that leftover was then converted to CO2 based off of the ratio of their G factors. Okay. And their G factors are just the fluorescence efficiencies of each molecule.
Probably with units of percent.
Yes, yeah. So in equation 2, the G is CO and the G CO2. Yeah.
Effectively rates.
Yeah. And so that's how we got the CO2 predator. yeah, the CO2 production measurements when we weren't able to get it directly.
Right. Okay. Good. I'm with you.
Yeah.
Okay. Different techniques. And how about?
Yes. And then figure 2 is the beginning of the more in-depth figures.
Okay. Let's go ahead and blow this up. There we go.
Yeah. So in figure 2, this is starting off with the CO to CO2 production rate ratios, which we have along the y-axis, and then along the x-axis, I have the heliocentric distance for when they were observed.
Okay.
And on the side, where all of the comets are listed, they're listed, and Centaur, they're all listed by their color-coded system. So the ones that are red are the Oort cloud comets.
Okay.
The blue ones are Jupiter family comets.
Okay.
The green one is a Centaur. And the purple one is a Halley type comet.
There you go. Okay, where's my greenie? There it is. Okay, anchor point. Okay.
And so there are a lot of interesting things that kind of pop out from this figure. The first thing I guess I'll focus on is the gap between 5 AU and like 6 point something AU.
Yes.
Yeah.
Nothing
so
there.
there's a lack of information that we have currently for objects that are that far out. And so it would be interesting to kind of see what happens, like if that gap was filled in a little bit more.
Yes. It's not because there's no objects there. It's just we haven't observed.
Yes, we haven't observed any objects when they were in that particular region. Yeah. And so looking at most of the objects coming in, you'll see that there's quite a few red objects, which are the Oort cloud comets. And as you look from 3.5 outwards, they seem to be CO dominated. Beyond 3.5 AU, it's just like all of it in the CO dominated region.
Yeah, right.
Oh, and what I'm considering CO dominated is when it has a ratio of CO production rate to CO2 production rate that's 2/3 or greater, 1 1/3 greater.
I'll believe the 1. Why the 1/3? Or is it 1/3? I mean, you can pick anything you want. I'm just curious why the 1/3.
Because we were doing the 2/3 for the bottom for the CO2 dominated one, and then 1 1/3 seemed like a reasonable place to kind of have like a little bit of leeway where it would be more CO dominated rather than CO2 dominated, or even an equal parts region. So it kind of it pushed it more to be more confirmation of a little bit more CO dominance.
Got it. It's almost like a safety factor.
Yeah.
There you go. Okay, I'm with you. Thank you.
Yeah, of course. And some of the error bars you'll notice are a lighter shade of blue than the black error bars. And that was done on purpose because those are considered dynamically new Oort cloud comets, which I'll describe in more detail in the next figure as well.
Okay.
Yes. And so looking at the Oort cloud comets again, but just below the 3.5 AU region, you'll kind of see that they're spread out amongst the 3 regions. So you'll see it in the CO dominated region, the equal parts region, and the CO2 dominated region.
Yes.
Which is kind of interesting. Like, it's interesting to find that it's like that diverse and spread out amongst them.
Yeah.
It was kind of expected. Yeah. Interesting. And the Jupiter family comets all tend to be in the CO2 dominated region. And I mean, since we don't see them that far out, we do have one measurement from 67P, which you'll see around like the 3.5 region, and that one's CO dominated at that point. Okay. But it's hard to say definitively like Jupiter family comets are gonna be CO2 dominated without more information filling it out there.
Right.
But going on to figure 3, I can start talking about the dynamical H's of the Oort cloud comets.
Ooh, there we go.
Sorry. I guess it's figure 4. Sorry. But in figure 3, I could just talk about figure 3 really quickly. I talk about the true anomaly, which I just look at essentially whether the comet is like a pre or post perihelion. That's another way of referring it to it when it's looking at the true anomaly. So I have it separated on both sides, and there wasn't anything too outrageous. It was actually kind of spread out about the same on both sides.
Yeah. Mm-hmm.
Yeah.
Pre and post. Uh-huh. Uh-huh. Okay, good. So no selection there, selection effect there. Okay, good. And we go back to the dynamical ages.
Yes. So for figure 4, where I talk about the dynamical ages, the 1/A0, I also put the semi-major axis on the top x-axis just in case.
Thank you.
Yeah, just in case somebody wanted to know, like, oh, how many AU is that? Like, yeah.
Well, it's 1/8, but yeah. It's
yeah. Sometimes the bandwidth isn't there mentally. Like, yeah, I get it.
Oh, it's too hard. I can't do 1/1. Okay.
Yeah. So I have the production rate ratios for CO and CO2 along the y-axis.
Mm-hmm.
And you'll notice that all of the dynamically newer objects tend to group around the CO2 dominated region again.
Yeah.
And dynamically older ones tend to be more CO dominated. And this is interesting because one of the reasons that we could see this CO2 dominance in the dynamically newer objects is possibly because of cosmic ray processing, which would explain why, like, the CO on the outside, let's say there's a lot of CO on the outside of these comets. Yeah, it could just be like worn away by cosmic rays.
Right. Okay. Good.
Yeah.
Okay. So older, more CO2. Okay, I'm with you.
Yeah.
And let's go to versus.
Yes, figure 5. Yeah.
No, this
so in figure 5, I start going into how the water production rate ratios, or CO to water production rate ratio, looks for comets. And this is where you'll see that we have more than 25 objects now. Yep. Many more.
45.
We have 45 objects for this figure right here.
Yep.
And so one thing that kind of stands out is how there's a little bit of change in the behavior of comets around, I guess, like 2.5 region. So, yeah.
Split this up a little bit. Yep, right around 2.5. We got a change the slope.
And this could be due to, like, because water production rate becomes more efficient as it comes. The water production rate of a comet becomes more efficient as it gets closer to the sun because it's being heated up more. Right. So it lets off water a lot more easily than it does when it's further out and it's colder. So around that 2.5 region, you can see that change, and it could be possible that it's for that. But when you look at figure 6, you'll find out, like, there's something straight. Like, if it happens for CO, why isn't that happening for CO2? But yeah.
Let's take a look at figure 6 there to do that comparison.
Yeah.
Okay.
So here you can see that it's more tightly correlated for the CO2 and the water production rates. They're more uniformly just kind of behaving the same. There isn't that separation that we see around that 2.5 region that we saw in the previous figure.
Right there. We got a definite break. Let's change the slope here. Not so much. A few outliers, but tighter.
Yeah. And I think it's definitely worth noting that there's, like, R2 is just its own object. Like, based off of the chemical composition of R2, it was going to be its kind of own person, as it were. You can see R2 is the red square at the top of the figure. That's just kind of, yeah. In the previous figure, it's also kind of there because it has a low water production rate. So it was never going to come down to meet the other comets.
Yep.
Yeah.
That one's a clear outlier on everything. Yes. Okay. Cool. I'm with you.
So then if we go down to figure 7, we see the CO and the CO2 production rates compared to water. So this is one of the ways that we can compare the total CO and CO2 compared to the water production rate. And here you can kind of notice, so I didn't fit the slope to this because I kind of want to see how it's going to shape out as we fill it out in the future. But what you can tell is that there is kind of a plateau around the 3.5 region.
Yes.
And again, this could be due to the water sublimation not being as efficient until that point.
Okay.
But it would be interesting to find out. And also we have very limited points, so it's hard to say that it's definitively a stable place or like a line if it's just three objects. Small number statistics, right?
Fair enough, right. Right. And we got a frost line in here somewhere, yes.
Yeah.
Okay. Good. Okay, cool. And figure 7, taxonomical families, heliocentrum. We already did that true anomaly. We did the 1 over A, 1 over AU, production rates, table 3. Ooh, additional measurements.
Yes. So this is where in table 3, I go over more of the water production. I go over the water production rates and more of the CO and CO2 that were used for figures 5 through 7. And so this is where you'll find the information for those other objects.
Got it. Okay. These are the additional ones. Very good. And then figure 8, CO.
Yes. So for the C to O, this was done by looking at the carbon-based species versus the oxygen-based species. Okay. So in this case, our carbon-based species were carbon monoxide and carbon dioxide.
Right.
And our oxygen species, our oxygen-based species came from all 3 molecules, since all of them bear oxygen. And yeah.
This is an abundance ratio.
Yes. Yeah. Based off of the productions, the production rates. Yeah. And so around here, you'll see that even though nothing was fit to it, like there is a bit of an increase in the carbon to oxygen ratio as we get a little bit further out.
Yes.
And yeah, besides that, we have 29P, which is our Centaur for the C to O. And it's the green object all the way around 6 AU. And you'll notice that there's a gap of information from around 4 AU to that 6.1 or 2 AU region.
Okay. And this red square and this green circle, are they high because oxygen is very low?
Well, yeah. So in the case of R2, which is that red square, it had a very low amount of water production rate. It had a very strange chemical composition, unlike other Oort cloud comets that have been previously seen, where water is typically the main driver of activity.
Right.
Yeah. But in 29P, that one is high because it has a very high amount of carbon monoxide. Yeah. And I think if you go up to figure 5 or 6.
Yeah, let's revisit that. Yeah. Let's revisit that. Let's go 6.
Yeah. So in figure 6, you can see that if we compare the carbon dioxide to water production rate, it's pretty low. It's like more water probably than carbon dioxide.
Yeah. Okay. Gotcha.
Yeah. And if we go up to the figure 5,
yes,
you'll see that. Yes. Yeah. That's where it kind of becomes a little bit competitive for water. Like it is more carbon monoxide than water production rate.
Okay. Okay.
And that could just be due to its location, but 29P is definitely a very interesting object to look into.
Absolutely. I'll follow up. Okay. Good. I'm with you. So where we were down and looking at CO ratios. Okay. Good. Trend. Overview of the families.
Yes. So I wanted to look at the traditional, so that's why objects are color coded, to see if we could find any behaviors that kind of stood out based off of their traditional dynamical categorization.
Yes.
And here we just kind of have a tally to put it into numbers, what we're seeing. So in the first column in table 4, you see the family class, the Jupiter family, comets, Oort cloud comets, Halley type comets, and Centaurs.
Okay. 4.
And then in the second column, we have the number of comets that were observed to have a CO2 dominated coma. And for JFCs, we had 8. Oort cloud comets 5, and in total we just had 13 objects that were CO2 dominated. And then in the next column, we have the CO dominated objects and mark out how many were in each category. And then in the one besides that, how much are like equal parts or comparable CO and CO2. Yeah. And then we also put out the total for how many we were getting there.
Good. So sort of a integration over the previous figures. Very good.
Yes.
Very good. Okay.
And in figure 9, we give the ranges of what we're seeing of the production rate ratios for CO and CO2 when they're compared against water.
Okay.
Yeah. And so you'll see that there's a really big range of CO compared to water. Yeah. And that big range could be due to having a larger sample size because we have 45 objects for the CO to water production rates versus the 25 CO2 to water production rates that we have.
Okay, possible.
Yeah.
Good. All right. Figure 9. And table 5 is sort of figure 9 with numbers.
Yes.
Okay.
And looking at just the objects that are under 2.5 AU.
Right. So the innermost ones. Okay.
Yes. Yes. Oh, and one key thing to kind of point out from this is that we're getting a CO plus CO2 to water production rate ratio of 18%.
Yes.
And that 18% is really important because that's what other papers have suggested could be an indicator of having primordial ices that are still conserved in comets. So it's like supporting that. Yeah.
Yeah, good. So it's consistent with those.
Yeah.
Very nice. Very nice. Figure 5. And this is how we do the CO ratio, given equation 3 here.
We have the carbon-bearing species on the top.
Yep.
And then in the bottom, you'll see that carbon dioxide is counted twice because it has 2 oxygen molecules.
Yes. Stereometric coefficient.
Yeah.
Figure 10.
Yes.
Okay.
So then another aspect that we took to look at the comets was looking at what has been typically considered carbon depleted and carbon typical comets by papers like from Ahern and also Anita Cochran, and comparing how that looked to what I had been seeing these comets as CO and CO2 dominant.
Yeah. And
seeing if there was any correlation. And yeah, there are some similarities, but there wasn't anything that was too final.
Good. So it's like a verification almost. Very good. Okay, so we're not out to lunch. We got a big figure here. We got here D.
So this is where I transition more to the area of the comet and their production rate ratios.
Oh, geez.
So in this figure right here, we have the carbon production rate, and we compare it to the area of the comet.
Right.
And we're still kind of using the same technique for color coding the comets that was previously used, where the purple objects are Halley-type comets, the red ones are the Oort cloud comets, the blue ones are Jupiter family comets, and the green are Centaurs. And in this case, I include an interstellar object, 2I. So that's the yellowish one.
Okay. Interesting.
Yes.
Where is that one?
Oh, and all of this is compared against like Hale-Bopp. I think that's something I forgot to mention. So the blue line is what we would imagine for the CO curve, and I put the particular diameter of 32 for this case. So if we had a comet that had a diameter of 32 kilometers, and we follow the CO sublimation curve, it would follow that blue line that we're seeing in the graph.
I'm with you.
And then the black solid line is what we would see for Hale-Bopp. And then the dotted lines above and below are if we have 10 times what we're seeing for Hale-Bopp, and then if it was a tenth of what we're seeing for Hale-Bopp.
Okay.
And so for the most part, a couple of different behaviors that you'll see is that the Centaurs are below the Hale-Bopp standards, kind of.
Right.
Yeah. Yeah, as well as the JSCs are. They're typically on a tenth of a Hale-Bopp kind of activity.
Yeah.
And or maybe on the equal parts region. Or cloud comets are a little bit all over the place, so harder to say.
They're all over. Yeah.
And for the interstellar comet, there isn't too much to say because we only have one object.
Yeah. But it's
so
high.
I can tell you something, but
it's
like,
high.
Yes, it is high. Yeah.
It's high.
Yeah.
It's telling you something.
Yeah.
I have to find out about that one. Okay. Very cool.
Mm-hmm.
Good. Okay. So that's figure 11. And then.
And in figure, for this table 6, I just list out the information that you're seeing in figure 11. Right. So again, in the first column, I have the comet names, and then the second column is the date when the observations were taken. Mm-hmm. The third column is the heliocentric distance for when the CO was obtained, the CO production rate. Mm-hmm. And then the fourth column is the CO production rate.
Yes.
Fifth column is the diameter size in kilometers. And then the sixth column is the production rate versus the diameter squared. Mm-hmm. And the final column is the references.
Very good. Mm-hmm. I like the meticulous referencing here. Very good.
Yeah, of course.
Ooh, look at that. Whoa. Okay. And figure 12, I think, is the last one in this lovely article. Okay.
So for figure 12, I did similarly to figure 11, where I had the sublimation the CO sublimation curve for an object that was 32 kilometers. Yes. I did for CO2 sublimation curve, but in this case, it's the sublimation curve for an object assuming it has a diameter of 10 kilometers.
Oh, different normalization. Okay.
Yeah. And then it follows the same color coding system of the Halley type comets being purple, Oort cloud comets being red, mm-hmm. Jupiter family comets being blue, and Centaurs being green. Yeah. And the dashed lines above and below the blue solid line are for if we assume 10 times more of this CO2 production rate versus the diameter squared. Okay. And then if it's a tenth of it. So trying to do something similarly to what we did for the Hale-Bopp curve in the previous figure.
Right. Some sort of reasonable banding. Okay.
Yeah. Mm-hmm. And so in this, there's very limited data for Centaurs and Halley-type comets. Right. But from what we see, the Halley-type comet does seem to behave like what we would see for a 10-kilometer object and its sublimation curve. Mm-hmm. For the Centaur, it's a little bit harder to say because it's an upper limit that we have.
Right.
So yeah. So we do have a range that it could be almost as much as what we're seeing for an object that's 10 kilometers, or it could be much less than that. Right. It's hard to say. Mm-hmm. The Oort cloud comets tend to be a little bit higher in terms of their CO2 production rates compared to the CO2 curve that I have plotted. Yeah. Mm-hmm. Mm-hmm. And the Jupiter family ones were a little bit harder to see as well because, yeah, you'll see that below 2AU, they're kind of, they're having more of the production rate for the area, while the further out from 2AU, it's less. Mm-hmm.
Right. Okay. Okay, cool. Okay, very good. And then the paper goes into detail on a number of specific individual comets, which is really nice.
Yes, so in there's an in-depth section for most of the comets. There are a couple that were not included in there. And I list out the comets that do not have their individual subsections, 144P, C1989X1. Yeah, all of those do not have their individual subsections, but the rest of them do. And I go over a little bit about what the techniques were that were used for those objects and a little bit of their background for each one.
Lovely. Very lovely. And table 7 is the last table, and these are our
yes. And that describes what we saw. And like that's the corresponding table for the final figure. Yeah.
Right. Very good. Very good. Go through some lovely detail there. There's our 4th equation. And the various comets. Lovely, lovely detail. Okay, let's do a summary. What do we get out of it?
So I guess there's quite a few things that you get out of the paper. One of the things that I guess I forgot to mention in figure 5 was that one of the reasons it would be very nice to see objects being observed, Jupiter family comet objects being observed further out.
Yeah.
But sorry, a little bit higher, please. Higher. Figure 4 or 3.
4. Got it. Okay. Dynamical age.
Sorry. One more up. Sorry.
3.
One more up, please.
2.
Yes. Sorry.
Okay. All good.
Okay. So in figure 2, one of the reasons that we might be seeing more Oort cloud objects versus the Jupiter family objects is an observational bias.
Yeah.
Since Oort cloud comets tend to be larger than Jupiter family comets, they have more activity out there, so it might be easier to be seen, and so that's why the Jupiter family objects aren't necessarily being seen as far out. Well, they might be active, they're just smaller and harder to catch.
Right.
Yes. Also, based off of what we're seeing in the dynamical age image or figure, we can see that the cosmic ray processing is one of the reasons that we could see that CO2 dominance, which is one of the main takeaways from the paper as well.
Okay.
Yeah.
Cool.
Yeah.
Very good. Yeah, with a study like this, you better have more than 1 or 2.
Yes, I have a couple more. Yeah.
We got 12.
And yeah, there's a bunch of other like really cool things that kind of came out of this. And I mean, finding that our results were in agreement with 18% of what that other literature has also seen.
Yes.
It's just kind of like, it's reassuring to a certain point. Yeah.
Absolutely. Absolutely. Anchor point. Very cool. Very cool. All righty. Olga, I want to thank you so much for walking us through your very lovely article on the world's largest survey of CO, CO2, water, and comets. Very good.
Sure thing, Frank. Yeah. Thank you for having me.
And you mentioned it a couple of times as you talked through, and so I'll push on a little bit. So where do you think we go over, let's say, the next 2 to 5 years on this topic? Is there additional observations that could be done either with JWST or maybe some upcoming telescopes that might be interesting, maybe Roman or something along those lines? Is there additional theoretical work that could be done on, for example, sublimation curves or things along those lines? And maybe there's even some laboratory astrophysics on, what is the production rate of CO and CO2 in the face of cosmic ray fluxes. So just sort of where do we go with this topic over the next 2 to 5 years?
Yeah, I think you brought up a lot of really good points with your question. So first off, I think with the dawn of JWST and all of the data that we're getting from that, that's a really great opportunity for us to get more CO2 production rates as well as CO production rates, since it has that capacity to get all of them simultaneously. And that's a really great opportunity. And hopefully, I'm working with a team that is getting some of that data.
Cool.
And
Good.
hopefully we will have another paper out soon that talks about a Centaur that has a CO2 production rate. Because as you'll see, there's currently only one Centaur that has been observed to have CO2 production rate, and that was 29P.
Right.
And so, yeah, hopefully that will be something to look forward to in the near future. But I think JWST measurements for sure will change the face of like everything that we're seeing, and it'll be really interesting to kind of fill out the figures and at different distances, because as you'll notice, there were parts of it that I think it would be really important to kind of get like from that 5AU region. If we had more objects to fill in there, it would be interesting to see if it follows that behavior for Oort cloud comets. if we were able to see Jupiter family comets a little bit further out from where we're currently seeing them, maybe in the 3 or 4 AU region as well, and just kind of see what their behavior is and see how that would fill in there. And I think there's a lot of lab work that could be done. It's not my area of expertise, but I would like to see what the papers say and like what their confirmation is based off of the conditions that a comet would need to endure in order to kind of behave the way that they do.
Right. Okay. Cool.
And I think a lot of theoretical models, I hope this paper kind of helps them in providing them data to test whatever they're seeing, because I think there's an abundance of data, as you'll see in the paper, that can be used for their models, and they could just kind of test whatever they're seeing with concrete data that has been used.
I like concrete data as opposed to quicksand data, you know? Concrete. Very good. Firm. Very good. Very good. Well, I really look forward to seeing this topic evolve over the next couple of years. It'll be very exciting to see these molecules. Very nice. Olga, I want to thank you once again for walking us through your very lovely article.
Thank you. Yeah.
And that will do. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.
Okay. Thanks. Bye.